In this video, I'd like to present a very gentle introduction to a piece of software named JFLAP, which allows you to do a bunch of automata theory. What we'll see in the video first is how to get a hold of JFLAP. Secondly, we're going to see a problem described to you, and then later at the end I will show you how to use JFLAP to solve that problem. First, how does one get JFLAP? We go to this address right here. Now, once you go to that address, to get JFLAP, you're going to have to fill out a simple form, just asking some information about you. And then after you do the form, you're going to have to go to the actual download site. I'm going to walk you through those steps in a moment. So if you clicked on the first address I had on the previous slide, this is what shows up. This is the home page for JFLAP, a tool that was built at Duke University to do automata theory. Now, we see its version, update things, bunch of information right here, but these are two things that we should notice right here. This is a link to get JFLAP, and this is a short tutorial how to use it. So were we to click on Get JFLAP, we would be taken to this eventually following the filling out of that short form. So here we are, and we're trying to get JFLAP, and this looks a bit confusing. It talks about changes and so forth, but really what we need is just to go right there. This is where you're going to click to get the version of JFLAP that's easiest to use on your machine. So you can ignore all the rest of this. What will be downloaded onto your machine is something called a jar file. You need not care about what that means. It also puts some graphics capabilities on your machine, and the jar file itself will be executable. So just download that guy and you're ready to use it.
All right, let's do a simple problem. First, we're going to design a finite state machine to solve our problem, and then we're going to show you how you use JFLAP to build the machine and run it. So let's consider the problem that we want to solve. We want to build a machine that accepts strings that meet a set of requirements. We're looking for pattern. And here are our requirements. The string has to have any number of A's, including 0, followed by any number, including 0, of B's. Finally, followed by C's, but there have to be an even number of C's, and then nothing else after that. All right, so those are the strings we want to accept. Anything else needs to get rejected. So, for example, the strings could look like this. There are some A's, then there are some B's, and then there are some C's. But remember, we also have to make sure that the number of C's is even. OK, so how do we start? We need states. What states do we need? Well, let's start with a state that corresponds to only A's so far, possibly nothing, but nothing except A's. We need a state that says, hey, we've already seen our first B. And that's important because once that happens, we cannot see any more A's. We need a state that says, hey, we've seen our first C, thus no more A's or B's. And the number of C's is odd, which of course it is when we've seen only one. But we need a fourth state to correspond to, and we're seeing C's, but there's been an even number of them. Of those, let's see when we say yes. We say yes when we've seen only A's, because remember 0 is an even number, so no C's is OK. We're good if we've seen A's and B's, again, an even number of C's. And then we're good if we have an even number of C's. The only one of these states where we're not going to accept is the case where we've got an odd number of C's. All right, so summarizing, those are the requirements, written little, so now we have some space to work on building our machine. We need state 1, And state 1 is our start state. And we know that that's going to correspond to only A's. Doesn't correspond to anything just yet except start, but let's see what we do with it. If we see A's, we can stay in state 1. Only A's so far. If we see our first B, we have to go someplace else. We can't stay in 1 because now no more A's are going to be allowed. So we go to this new state we're calling 2, corresponds to this, at least 1 B. And in this pattern language, it doesn't matter how many B's. So if we see additional B's, we just stay in 2. They don't count in terms of making a decision at the end of whether the string is acceptable or not. So we just stay in state 2. Now, if we see our first C, we're going to have someplace to go. So let's create state 3. And if we see our first C, we go there. This corresponds to the case where we have an odd number of C's, in particular 1. But we'll generalize that later. And note that we can also go there if we see a C from state 1, because nothing says there have to be any B's. All right, so state 3 corresponds to the case where we have seen right now. It corresponds to the case where A's and B's, if there are any, have been in the correct order, and there's now 1 C. What happens if we see more C's? How about this? Can we do what we did in the other cases and just loop? Oops. The problem now is we really do care how many C's. Not exactly the number, but we care whether it's been odd or even. So if we see a second one, we cannot simply loop in 3. So this requires that we build a new state 4. There you go. And let's build the transitions to it. If we see a C from 3, we go to 4. And if we see a C from 4, we go back to 3. So we're just going to alternate between 3 and 4. Odd, even, odd, even. And we need to decide which of these states are accepting states. Note that I've marked 1 as an accepting state by putting this little circle here. If we have seen nothing yet, that's okay. If we've seen only A's, it's okay. I've marked state 2 as an accepting state. Remember, again, we've seen A's and then B's, at least in that order, nothing out of order. And remember that 0 is an even number, so we've seen an even number of C's. What about the C situation? 4 is an accepting state, because that's the case where we had even numbers of C's. By the way, note that there's no way to get to 4 from either 1 or 2, because that would mean that there was a single C, and state 3 is capturing the case of a single C. So there you go. I've just copied our machine over onto this so we can see it in a bigger picture of it. Let's look at this, and you may be saying, well, I don't get what happens if you did get, say, A's, then B's, then maybe another A. That is a possibility. It's something we need to reject, but it kind of looks like we haven't even accounted for that possibility. So let's think about that. To do that explicitly, what we need to do is to create a 5th state. And we often call it the dead state. It's the state in which we've made up our mind that the answer is no. And in this formalism, you don't actually send back an answer until you've read all of the symbols. So the dead state is, hey, I've made up my mind that the answer is no, and now I'm going to dutifully come over here. And as I read the rest of the symbols, I'm simply going to stay there. And when I run out of inputs, I'm going to be in a state that's not an accepting state, and I'm going to say no. So look, I go to the dead state if I'm in 2 and I see an A. That means an A came after a B. If I'm in 3 and I get an A or a B, that means I got A's and or B's after C's, and the same thing here. So those are the cases where I immediately know that the letters are out of order. I go to the dead state, and I dutifully stay there. Now, why didn't I put this 5th state on the machine that we originally designed? Because it's common to use the convention, and JFLAP does, that you don't have to write it. Okay? That it makes drawing the pictures complicated. Often lines have to cross each other. So we will use the convention that there is a dead state. If you ever go there, you stay there. And you go there whenever you're someplace and the transition that you might need, like in this case A, is simply missing. It is an implied transition to the dead state. So when we build this, in JFLAP, we don't have to write the dead state explicitly. We can write just this, as in fact we did. And it's equivalent. It's just a neater way of saying it.